Okay. Actually, let's do some more technology check stuff. Uh, did you guys, or were any of you guys try to look at the recording at all? Okay. Maybe you guys didn't need to, but if you did it look okay? It was fine. Cool. Did any of you guys try to look at the OneNote that I shared on that announcement? Did that look okay? Cool. This is actually kind of exciting because this is the first time I've taught this class and actually just shared my notes, and I guess that's sort of a nice a nice feature of this whole weird remote situation that we all have. Some other sort of class business then, based on your responses to the polls for office hours, my office hours are going to be on Wednesdays after class, immediately after class. We can probably just stay in this room. No one's going to kick us out of the Zoom room, I think. Um, and then the TA office hours, as I mentioned, one of them will be on Tuesdays at 3. That's what was sort of scheduled on the registrar. And then the other one is going to be on Mondays at 7. Okay. And on the homeworks, it says who the TA is in charge of that particular homework set. And so it'll be that person basically taking care of both office hour sessions. And then that person can help answer questions and stuff like that. Canvas has a feature that I've never used before. Maybe you guys know more about than me, called discussions. I might refer you guys to that, especially if, you know, before office hours or even during office hours and stuff like that, if you have questions and stuff. And, you know, almost certainly you're not going to be the only one that has that question. So like if you guys send me an email, or I might ask the TAs to do this, if you guys send them an email, they might just be like, can you please post that on Canvas? And then we can do a discussion or something like that. So, and, you know, feel free to answer each other's questions and stuff. We're trying to do the best that we can to make this weird remote thing be as like cohesive for everyone as possible. Zhao, you don't have to be here if you don't want to. This seemed to work okay, but if you want to stick around, that's cool. What else was I going to say? So those were the office hours and stuff. Let me see. We're going to start trying to do in-person classes on Monday. It's probably going to be, just to give you a quick preview, they have technology and stuff set up that lets me like blast my voice across the whole screen so I can still talk through a mask and so you can still hear me. Or throughout the entire room. That same audio will connect over Zoom. I'll probably basically just sit there with my tablet and then write, and so it won't be that different from what you're seeing right now, except all of us will be together, and so you can ask questions and you can sort of at least see each other and stuff. Just quick show of thumbs. How many of you are preliminarily thinking about coming on Monday, and how many of you are thinking about staying home?
Is it thumbs for coming on Monday?
Thumbs for coming, yeah. Thumbs for coming. Okay, cool. Well, it'll be nice to see some of you guys in person. I hope we can all stay safe and, you know, follow all the guidelines and everything. But otherwise, I think it'll be really fun. Okay. Last bit is just that homework 1 was already posted. I think I already got a question the other day on it. Feel free to get started. It's basically going over these sorts of vector and tensor things that we've been talking about. Okay. So I'm going to go ahead and start sharing my OneNote. Any questions overall on how this stuff all works? I'm going to keep going then. So, whoops, here we go. You guys can see the shared screen right now, and you can see my cursor, correct? Cool. So we introduced index notation on Wednesday. Give me a thumbs up if you have seen index notation before. Okay, good. So there are very few of you, which is great. And then give me a thumbs up if you're a little confused about everything we've been doing with index notation so far. Sweet, me too. Okay, and so I'm going to try and break a little bit of that confusion. We haven't really talked very much about specifically how index notation works in terms of different rules and everything. Maybe you guys have seen some of these implied rules. And so let me just introduce in general how index notation is supposed to work. Okay, so I'll just say index notation rules. Notation rules. Okay. The first one, if it's not apparent already, is that we're supposed to sum over repeated indices. Okay, so I'll refer to this expression, to this previous expression. I'll write that down again in just a second as another example to go a little bit more in detail with this. But whenever you see like a term and you see repeated indices, like let's say this one, for instance, then this just means that you're supposed to sum over j from 1 to 3, right? The other rule, there's really only one other rule, and this rule has a couple different components, basically. I'll say 2a. I'll say for expressions, and by expressions I mean like a single term, or just like, you know, in the equation f equals ma, then ma is an expression and f is an expression. The equation is f equals ma. Okay, that's what I mean when I say expression. Okay, then that means unit vectors are implied for free indices. Okay, and so for instance, if I have the very simple expression ai, then that is equivalent to, right? To do this, to arrive at this, I applied rule 2a, which means that there's a unit vector, and that unit vector is going to be the same index as my original index because it's a free index. And then I sum over that. So I sum over I like that. The corollary to that is that the number of free indices determines scalar or vector. Right? So if I have something that's just like a row with no index, then that's clearly a scalar, right? This is a scalar. Right? If I have something that's like AI, as I wrote over here, then that's clearly a vector. And later on in today's lecture, we're going to talk about tensors, and those are going to have two free indices stuff. Okay. Rule 2b is that for equations, the free indices must match. Okay. This also follows from like logically from rule 2a. What I mean to say is that if I want to say that like two vectors are equal to one another, then the way I write that is AI equals BI. Okay. Another way of writing this, when I write AI equals BI, what I've actually written is three different equations saying that the three components of A are equal to the three components of B, right? Now, I could also have basically, I could also have applied rule 2a here to basically mean that the left side of this could also mean that the left side is sum over AI of EI, right? And the right side is sum over BI times EI. And this is notation that you guys already know. This just says that these two vectors are equal. And the only way that two vectors can be equal is if their components are equal, right? And so that's why in shorthand, we typically just go off of something like this. Okay. And so this expression makes no sense. Okay. This expression right here makes no sense. Likewise, also like this expression makes no sense either, right? It doesn't make sense to take the ith component of A and then subtract it from the jth component of B. It makes a lot more sense for me to to say that, right? So let me just write that down for the benefit of people that will look at this later. I'll just say that do not, or I'll say these do not make sense. Okay. And then rule 3, it's not a real rule. It's something that you guys, that just sort of follows from the definitions, is just follow the rules of Kronecker deltas of delta and epsilon. Okay, the permutation symbol and the Kronecker delta, right? And so, for instance, the Kronecker delta has something called a sifting property. So what that says is that, for instance, if I want to take the dot product of two vectors, okay, then I can write that. Remember, the definition of the dot product of two vectors is you first do delta ij times ai bj, right? Now, from the rule above here, you can stare at this expression right here and realize it's a scalar, right? Because there are no free indices, okay? And then the sifting property of the Kronecker delta means that basically I'm summing over I and j here. Remember, we're summing over all the free indices, and so I'm summing over I and I'm summing over j. This means I get to eliminate one of the sums, because as we discussed in the previous lecture, the Kronecker delta is special in that only one of those three terms in the sum is going to be non-zero. Okay, and so then this allows me to, for instance, basically transfer this j, or turn this j into an I, or I could turn this I into a j, right? I could call this basically AI, BI. So in other words, I'm turning this j into an I using the Kronecker delta. Of course, I could also turn this I into a j, and then I would get AJ, BJ. That's the same thing, right? You guys can kind of see, well, I'm summing over the free index anyway, and so it doesn't matter what the index actually is. So in general, I can make the summing, or I can make the repeated indices basically anything that I want, and it should still work out just fine. Make sense? One thing that I haven't written up here is that here's another expression that doesn't make any sense. That should say a C, sorry. It doesn't make sense to have a repeated index 3 times. Okay, you almost never, you basically never see that in index notation. Okay, so these are just kind of things to let you like as you're playing around with index notation. If you ever get to a point where like something like this happens, or something like this happens, then you know that something weird really happened here. Okay, so let me actually go back just to completely drill home this index notation sort of thing. Let me just go back and look at the previous example that we have. And that was this vector triple product. Okay, and then just applying this the direct rules of what a cross product actually is, we were able to arrive at this expression. Okay, and the way we did that is because when you take two indices, or when you take two vectors, let's say A cross B, then that's defined as epsilon I j k a j b k, right? Another way of saying this is we know A cross B is equal to a vector, and so the ith component of that vector is given by this expression, where I'm summing over j and I'm summing over k, because those are implied, right? Another way of saying this is the right-hand side of this expression, there's a free index I, and so there is an implied E sub I unit vector, and I'm summing over that as well. Okay, and so this quantity over here is a vector, right? And then if I just substitute that into here, then what I have is, the cross product of B and C is therefore this, or the kth component of the cross product of B and C is this, right? Where I'm summing over M and N because those are repeated, right? And then I want to take another cross product of that. And so then I need to take the jth component of my first vector A and the kth component of my second vector B cross C, which is this, and then I cross product those together. And then therefore the ith component of this whole thing is just this, right? And then what you guys will find, and then of course this is just a term, right? And so I'm just, there are X number of terms in the sum. And so I can do all my commutation and stuff inside this term. And so this is just the same as I wrote yesterday, epsilon ijk, epsilon kmn, aj bm cn, like that, right? And what you get from your homework is that these two things multiplied together is an identity. Like that. And then we can use Kronecker deltas to figure out what all of these things are, right? And so we distribute out the two terms first. So if we take, let's say, this term and multiply it with this, then that means I can use the Kronecker delta IM to turn this BM into a BI, right? Actually, I'll keep things in the same order as they started off over here. So this is a AJ. I'll take this BM and turn it into a BI. And the CN, I'll turn into a CJ. You might ask, wait, Mitchell, why did you decide to turn this, why didn't you use the delta JN to turn this AJ into an AN? I could do that too. Then this would just say AN CN, right? But I'm summing over repeated index anyway, and so it doesn't matter whether this is AN or AJ, right? And then I can do the same thing on the right-hand side, or on the other term, okay? And so over here, what I have is, I'll let AJ again stand. BM, I will use the Kronecker delta to turn this into a BJ. And then CN, I'll turn into a CI. Notice how whatever I do, the free indices always match, right? So this is an equation, right? The left-hand side of this equation is basically this over here. See if I can figure out how to do that. Whoop, cool. Okay, never mind. That's way too complicated here. Let me see if I can do that. I might be able to copy this. No, okay, never mind. The left-hand side of this equation is this thing up here, right? There's only one free index in this whole expression. That's just I. Everything else is repeated. So this is a vector, right? There's only one free index over here too. That's also I. Okay, and if we decide to convert this back into things that we're more familiar with, then this is the repeated index. We're summing over that, right? And so AJ, CJ is just a scalar, and that's your dot product. Okay, another way you can think about this is, you know, when you dot two vectors, you just multiply their components and add them all together, right? That's literally what we're doing here. We're multiplying the jth component of A and the jth component of C, and multiplying those together and then adding them all up. Okay, and so that's why this is just vector B times scalar defined by A dot C. Okay, and then this one on the right is C is a free index, or C contains the free index, I guess I should say. So here's C, and then we have A dot B. Okay. Did that at least resolve some of the confusion that you guys have with the next notation? You guys can kind of see how this overall works again. And you'll get plenty of practice over the coming few lectures, next few days to weeks. Okay, and something that will maybe make it even more clear is when we actually start getting into tensors, which is what we're going to get into right now. Okay, so a tensor, I'm going to write in this class, tensors are usually going to be denoted as capital letters. Sometimes I'll use Greek letters. There's a specific case I'm thinking of later on in the class. And they're always going to be underlined twice. Okay, and a tensor is an entity that looks like this. You can think about it as a vector of vectors, where like a vector has three components, right? Each of those components is a scalar. A tensor is like a vector of vectors, so it has three components of vectors, each of which have another three components, so it has 9 components. Okay, and the way we write it is these two unit vectors basically just smushed together. Okay. I'm not doing a dot product of these two unit vectors. I'm not doing a cross product. I'm just smushing these two unit vectors together. Okay. And so if I were to write out this tensor, I will have to write out 9 different things. I'm not going to write out all 9 terms because that gets real boring real quick. But I'll write out the first couple. And then etc. Right? It goes all the way down to this. And so you can see how there are 9 components to this, right? Here I can write out the 9 components. One way that people like to express tensors, it's not exactly the same thing, and there are some things of some ways of confusing yourself when you do it like this, but you can write a tensor as a matrix. And as engineers, we've all played with matrices enough before to kind of get an idea of what a matrix actually is. Okay. Now, we just talked a lot about index notation. We just spent like maybe 15 minutes going over that, right? And so I can express this in terms of index notation by getting rid of the sums, or as I mentioned, even better, we can just completely get rid of the unit vectors too, okay? And so this is in index notation. I'll mention that smushing these two guys together is a special thing. It's called a dyadic product, actually. And it's a special operation. It doesn't actually do anything to either of those vectors. Okay, so it's not like, you know, e1 dot e1 is equal to 1, or e1 dot e2 is equal to 0, like those things that you guys are familiar with, right? And in fact, e1 e2 is different than e2 e1. Okay, and that's why there are 9 components to this, not 6 components, right? Because if e1 e2 were the same as e2 e1, then, you know, I would have a few repeated things in my little matrix here. Okay, so I should mention, I guess there's something called a dyadic product. Okay, that's in non-index notation. That's just taking two vectors and smushing them together. Or in index notation, I can write that as aibj. If you think about it, this quantity right here is a tensor. Okay, it has 2 free indices. Okay, the way that we would write this in matrix form would look something like this. Okay, and perhaps here you can see why E1, E2, E1 is not the same as E1, E2, right? Because, you know, a priori, without knowing what A1 and A2 and stuff like that are, there's no reason why this term is going to be the same as this term, right? Okay, we've actually been playing a lot with a tensor already. There's something called the, not int, sorry. There's something called the identity tensor. If I can write better. Called the identity tensor. And that's given by this. Or some sources like to call it this. We'll use that plenty in the class as well. The identity tensor in index notation looks like this. You guys have seen that before, right? That's just the Kronecker delta. And in fact, the Kronecker delta is actually just a tensor. If you think about it, it has 2 free indices. If I want to write it out like a matrix, it would look exactly like this matrix, except it'd be zeros everywhere, except for the diagonal would be 1. And you guys have seen that before. In the past, you might have called that the identity matrix. Okay. So as I mentioned, tensors are kind of like vectors of vectors. Let me show you why that's true. So if we want to look at the components of a tensor, right? As we know, vectors can be written like this. right? This is the component of a vector. Like the ith component of a vector A, you can get by just dotting that vector with that unit vector, with the ith unit vector, right? And so if I wanted to dot a tensor with a unit vector, then I should get a vector, right? Because as I mentioned, the components of a tensor are vectors, right? So let me do that. If I take just any regular tensor here and I dot it with, let's say, the mth unit vector, I'm getting into m's because I don't want to confuse I and j's and stuff like that, right? Okay. Then I can calculate that real quick. Let me just expand out, and I'm going to write out the unit vectors here to reduce confusion. Remember, this tensor is aij ei vector dyadic product ej vector, right? Dot that with em. Then the way it works is, the reason why I smush these guys together is when I take dot products, I just dot the closest thing. Okay, that's the rule when it comes to tensors. Okay, and so then this just becomes aij, okay, ei, and then I have ej dot em, which, as you know, when I dot two unit vectors together, I just get the Kronecker delta, right? And according to the Kronecker delta, then this just equals aim ei. Okay, so you can see how when I dot, or basically the mth component of a tensor is equal to a vector. Okay, so I'll say the component of A in the mth direction. So this is just like, if I want to say what's the component of a vector A in the x direction, right? Here it's the component of A in the mth direction, either x, y, or z, right? Is a vector A1m E1 plus A2m E2 plus A3, I'm sorry, my pen is kind of acting up, plus A3m E3. Okay. Now, of course, this is a vector, and so I can take the component of a component again, and that's what gives me my individual, like one of my 9 tensor components, right? So for instance, I could then take the kth component of this vector that I wrote out, right? And the way that I would calculate that is this. If I dot this again with k, then that's just, well, whatever I had written up here, this is aim ei dot ek, right? And by the same rules of, dot products and Kronecker deltas and stuff, then this is just akm. Okay. So that's kind of cool. I mean, a tensor is basically just, it's like a higher order vector. Like I mentioned, it's a vector of vectors, and it obeys all the things that we're already very familiar with, which is, if you dot it, like if I want to find the kmth component of a tensor, then I dot it with m and I dot it with k, the unit vectors of those, right? And so some of the things that I'm implicitly not mentioning, but then I'll get into a little bit more detail now, are you can do operations on tensors just like you can with vectors. And we will do that a lot in this class. Okay, so basically a dot product follows the same rules as vectors. Okay, so for instance, if I have a dot a like that, then in index notation, that's just a sub I aij. Okay, by convention, when I write a dot a, then then it's the closest index to it. Okay, and you guys can tell me, or you guys can maybe figure out that this quantity right here, is that a vector, a scalar, or a tensor?
Would be a
It's a
vector.
vector, right? Okay, because there's only one free index. It's just the index j. Okay, so the result here is a vector. Likewise, I can also take a dot product on the other side. And then again, by convention, I dot it using the index that's closest to it. This is also a vector, okay? What I'll note is that this is not the same as a dot a, as little a dot tensor a. Okay, you can see how perhaps here it's not really the same. And to convince yourself that this is not really the same, you can write out the different components of this vector. Okay, so let me just do that real quick then. This vector right here is basically the first term or the first component of this vector. I'll say, you know, the actual vector here looks like this, right? And so if I want to look at the first component of this vector, then this is basically just a1, a1, 1 plus a2, a2, 1 plus a3, a3, 1, right? See how that works? Look confused if you're not confused, or give me like a thumbs down, or like if you guys don't see how I got that expression. Does this kind of make sense? What I'm basically doing here, how I got from here to here is, well, if you look at this expression, remember free indices have a unit vector associated with it, right? So that's where my EJ comes from. And then I'm summing over I and J here, right? And so the first component, I'll say the E1 component here is where I'm only looking at the J, I'm only looking where J equals 1, okay? And then I'm summing over I. So that's where I have, that's why I have A1, 1, A2, A2, 1, A3, A3, 1. The full vector will be this times E1 plus yada, yada, yada times E2 plus yada, yada, yada times E3, right? Does that kind of make sense? Okay, well, this quantity right here is different than that, because this quantity is like that. Okay, and so if I were to write out the E1 component of that, then I would put a 1 right here, and then my E1 component will look something like this. Right? See where that comes in? It's because I'm summing over J, and so my J, and so, you know, when I'm looking at my E1 component, then my I is going to be equal to 1, and then my J goes from 1, 2, and 3. And you can see how this quantity here is not the same as this quantity. Now, there are situations where these two could be the same, and I'll get to that in just a second. Okay. Now, you can also, so basically you can do dot products as much as you really want, okay? And they work basically the same as vectors. You can also dot two tensors together. Okay. And this looks like this. If you're confused about how that happened, then write out what A is equal to. Remember, A is just equal to this. Okay. And then write out what B is equal to. B will be equal to the same, although I wouldn't reuse the indices because then your sums get really confusing, right? So, call A something like Aij, and then call B something like BMK or something, and then actually dot those together. And then your unit vectors will dot together, use a Kronecker delta, and you'll get an expression that looks like this. Okay, I encourage you to play with that on your own at home. So the result here, though, we should be able to figure out together, is this a scalar, a vector, or a tensor? This is a tensor, right? That kind of makes sense? Because this is a repeated index and the only free indices are I and K. So this result is a tensor. Okay, you can do the same thing for cross products as well. It's just a little bit more complicated with the whole epsilon thing, the permutation symbol, but it basically works out the same way. Okay. There are special tensor operations. So there are special operations that only work on tensors, and we will use those throughout this class as well. So let me just write those down right now. Okay, you can do a transpose. This is kind of like transposing a matrix. Okay, so if A is defined as Aij, right? Then A transpose is defined as Aji. Okay. Now, what's implicit, again, in all of these expressions is for every free index, there's a unit vector associated with it. And so this expression is actually sum over Aij times Eiej, right? Just like how this expression is basically sum of Aji also times Eiej. Okay, and that's why these two things are different. If I wanted to write out the matrix form of this, well, it's just a transpose, as you guys might have seen with matrices. So this would look like A11, A21, A31, A12, A22, A32, A13, A23, and A33. Okay, and in fact, this is one of the reasons why I find matrices as a kind of a confusing way of writing tensors, because I can never figure out which way to write it to transpose it. But if you just write it out like mathematically in index notation, then you don't need to keep track of any of that stuff. Notice how this expression here is different than this expression up here, right? This one going down this way, this is A11, A21, A31. Going down this way, this is A11, A12, A13. Okay. So what I'll note is that in some cases, the cross product of a vector and a tensor actually is commutative, right? But that's only if A is equal to A transpose. Okay, that's maybe not surprising. Remember from this analysis that we did up here, right? We found basically what the first component of these two quantities are, right? And the first component in little a dot big A is this, and the first component of big A dot little a is this. Well, if A21 is equal to A12 and A31 is equal to A13, then these two quantities are actually equal, right? So this is in general like how you can show these sorts of relationships with these tensor things. Like whenever we ask you, for instance, in the homework, we ask you to prove that identity, right? Just look at the different cases and stuff and show that it actually works out. Because just in general, when two things are equal to one another, when two tensors are equal, or when two matrices are equal, or sorry, when two vectors are equal, you just need to show that those components are equal, right? In the homework, what we're asking you to do is show that this quantity is equal to this quantity, right? Another way of writing this, or another way of saying this is, well, this guy right here, does anyone know what this quantity is? This epsilon ijk epsilon KMN, is it a scalar, a vector, or a tensor? We'll call it a mega tensor. Okay, it's actually a rank 4 tensor because there are 4 free indices. Okay, you could, if you had a quantity like this, we don't think about this in fluids. We do think about 4 tensors in general relativity, but we're not a class on general relativity right now, right? But you could write this expression out as epsilon ijk epsilon kmn times ei ej em en, right? And there will be 81 terms because 3 to the power of 4 is 81 in this tensor, okay? And it'd be a giant mega matrix that goes out into 4 dimensions, to 3 dimension space and 1 of time or something, okay? And in your homework, you're trying to show that this is equal to this, which is also a 4 tensor, right? And so what you could do in your homework, which I strongly recommend that you don't do, is show that every one of those 81 components are equal to each other. Okay, please don't do that. But what you can do is look at specific cases, right? In certain cases, one component's always gonna be equal to another component and stuff like that, and then show that it's true for all the different cases, okay? Sort of like what we did over here, right? Where it's like, oh, okay, the one component, it seems to be true, and then by analogy, all the other components should work out and stuff like that. Does that make sense? Okay, cool. One more special tensor operation. There's something called a double dot product. Okay, that's just a dot product twice. So you just take 2 dot products. Okay, so if I have 2 tensors, that's represented mathematically as a colon, just because there's 2 dots in a colon, okay? Then the way we write this is, okay, so if we have a tensor aij, and I'll write out the unit vectors again here, double dotted with bkm, like that. I'm gonna, these things can, these prefactors can come out. I'm only gonna look at the unit vectors now. I'm basically dotting the 2 unit vectors twice. Okay. So what I do is I take EJ and I dot it with EK, and then I take EI and I dot it with EM. Okay, fairly straightforward. This is what I mean when I say I dot it twice. Okay, and so if I were to do that, then I get EIJ BKM. The dot product of EJ and EK, whoa, sorry. Apologize, hopefully I haven't lost you guys. The dot product of EJ and EK is delta JK. And the dot product of EI and EM is delta IM. And by the rules of Kronecker deltas and everything, you know that you can then replace this K with a J because there's a delta JK. You can replace this M with an I because there's a delta IM. And so this is just equal to AIJ BJI. And is this result a scalar, a vector, or a tensor? This is a scalar. Okay, so this is a scalar. Okay. All right. Just one more. There is something in for tensors that's called a trace. This one's really easy. Okay, that's written as the trace of a tensor is just this. Okay, this is also a scalar. What this basically says, remember, sum over repeated indices. Okay, now it's weird that these 2 indices are under the same umbrella here, but you know, I'm just summing over both of these. Okay, and so this is A11 plus A22 plus A33. Okay, so that's just the sum of the diagonal components of this tensor. Okay. So some special things that happen with this, or just some special properties of tensors. there is something called a symmetric tensor. Okay, a symmetric tensor is basically this, where A is equal to its own transpose. Okay, so a symmetric tensor obeys that. Okay, there are cases in fluids that we'll get to later on where there are tensors that are always symmetric, and it makes our lives so much easier. Here's one reason why it makes our lives so much easier. When you look at a typical tensor, this is a transpose of A, it has 9 components in it, right? But if it's symmetric, then that means that this component is the same as this is the same as this, and this is the same as this. Okay, and so therefore there are only 6 independent components, right? So a symmetric tensor only has 6 independent components. Okay, there is also such thing as an antisymmetric tensor. Okay, that is, well, it's just analogous. It's where a tensor is the negative of its transpose. Okay, if a tensor is the negative of its transpose, then glancing at this again, that means that A21 is always equal to negative A12, A31 is always negative of A13, etc., right? It turns out that this tensor would only have 3 independent components. The reason is because what this also implies is that A11 is equal to negative A11, which means that A1 has to be equal to 0. And so all the diagonal components have to be 0. Okay. So this has 3 independent components. Okay. And therefore it has 0 diagonals. Okay. And then one thing to note is just that all tensors are sums of a symmetric, if I can write, sorry, and an antisymmetric tensor. Okay. It does halfway make sense, maybe, right? Because if a symmetric tensor has 9 independent components and an antisymmetric has 3, then if I sum those two together, then I get 9 independent components, and that's what a typical tensor should have too, right? And I can write that pretty easily, actually. I can, like, once, if you give me a tensor, I can actually figure out what those components actually are. Aij can be written as this. Okay. All I basically did is I took my Aij and I split it in half and then added them together, and then I added and subtracted a negative, a plus or minus 1/2 Aji. I'm sorry, this looks terrible. Aji. Okay, and then maybe it's apparent that this piece right here is symmetric. And this piece is antisymmetric, right? Because if I only look at this piece and I switch the I, and the J, then this looks then this doesn't change. If I only look at this piece and I switch the I and the J, then I have to take the negative sign of it. Okay. Now, in non-index notation, that can be written like this. Okay. And so this will be important later on in fluids. There are special tensors where where it does make a lot of sense to break it up into the symmetric and the antisymmetric component. And each of those things actually means different things. Okay. All right, it's 3:50. I could theoretically go on for another 10 minutes, but that wouldn't really be fun. Wish you all a happy Friday. Any questions on this lecture or anything that's or anything going on in the class or just general life things? If we want to go into too general of life things and too personal things, I can stop recording if you want. All right, I guess not. Hope to see some fraction of you guys on Monday. Again, don't feel like you have to come at all. Hopefully you'll get just as good of experience at home. It'll look pretty similar to what you've had today. Otherwise, have a good weekend. I'll see you on Monday.
Good weekend, Professor.